So hello again, this is Roger Koch Barr, and this is the Bioelectricity course, week 6, and we have reached lecture segment number 6. With action potentials, it's not just an action potential. There's an action potential and another and another and another. It's the number and the speed of the action potentials that carry information from one place to another. Sometimes they carry actual material, like a freight train, moving calcium around, moving some other substance, releasing it or keeping it under control. So sequences of action potential are of high interest as far as function. Here we'll look at what is called S1, S2 stimulation. Stimulus 1 followed quickly thereafter by a second stimulus, and ask what happens as the interval between the first and the second changes. So here it is with the stimuli separated by 15 milliseconds. Seems very straightforward. Give a stimulus. You notice a good strong stimulus magnitude. We give a second stimulus. Second stimulus is given 15 milliseconds after the first. Well, look what happens, just what you'd like to see happen. After the first stimulus, after this one, we see an action potential at I. We see the action potential propagate down the fiber, so we have an action potential at J. And I'm sure it continues right on down to the right end. After the second stimulus, we see an action potential at I, followed by a second action potential at J a little bit later. Goes right on down the fiber, just like before. Everything is working just like we want it to. We are happy. But now, look. We move our stimuli a little closer together and disaster ensues. Here's our first stimulus. Everything is good. We have an action potential at I and an action potential at J. Then we give our second stimulus. Here is the response at I. Pitiful little response. No response at J. Nothing. So it worked the first time, but it didn't work the second time. Rats. Let's look at the membrane itself, at the mechanism, and see what's happening. You recall from the discussion of the Hodgkin-Huxley model that what happens in the membrane is controlled by probabilities M and H for the sodium current and probability N for the potassium current. Let's look and see how those have changed as far as the first stimulus compared to the second. For the first stimulus, variable M is pretty much at the baseline, and then the stimulus moves it way up there. So M is greatly increased by the stimulus itself. For variable H starts off pretty high, and although it falls rapidly, it's still pretty high at the end of the stimulus. So I and A for the first stimulus, for the first stimulation, we have M cubed H times Vm minus E and A. M cubed H is pretty good. For the second stimulus, now we're on the second stimulus. M starts off about the same place, but it ends up so much lower. Was here at the end of the first, and it's way down there at the end of the second. M just ends up so much lower. H ended up here first? Well, it starts off a little lower and goes lower still. So it's not a tremendous change, but it does go downhill. So for the second stimulation, what we have, taken as a whole, we have I in A, second stimulation, M cubed H. Both M is lower and it's cubed. Look, it's much lower. H is a little lower. So M cubed has a big effect, H a small effect, and the result is the sodium current is much less than it was before, because both M cubed and H are smaller. That is to say, the probabilities are smaller. Turning that around in terms of sodium current, it says much less sodium current is able to come into our fiber as a result of the second stimulus. Now let's look at potassium. So with potassium, we see that for the first stimulus, at the start of the first stimulus, we're here, and then as we stimulate, we wind up maybe up there. So HK1 into the fourth times Vm minus Ek. Pretty good size. In any event, we use it as our reference point. For the second stimulus now, we start off higher. We end up probably about the same place. So Ik 2 into the fourth. And now Ik is probably, Ik is bigger. So with our first stimulus, we made sodium big and kept Ik moderate or small. In our second stimulus, we made sodium much smaller and made Ik either unchanged or bigger. So no wonder our second stimulus didn't do anything. We couldn't get enough sodium current to make something happen. So let's just say that in words. For the stimulus to produce an action potential, at the end of the stimulus must have made the sodium current greater. Let's make the sodium current greater than the potassium current so that Vm keeps on rising. Sodium is bringing positive charges in, potassium is moving them out, so they have to be coming in faster than they're going out so that Vm can keep on rising. And that's what happens with the first stimulus. At the end of the second stimulus, the situation was that INA was lower, Ik was higher, or maybe about the same. So because INA changed so much, INA did not exceed Ik at the end of the second stimulus. Consequently, there was no subsequent rise of Vm, nor was there a second action potential that occurred thereafter. We gave the stimulus, but the fiber wasn't ready. That's another way to think about it. When you give the stimulus, there can be an action potential if the fiber is ready, if the membrane is ready, if it's recovered from the first, recharged its energy stores, and ready to do the second. This can have a beneficial effect, but in any event, it's a big effect. You can only give action potentials so fast. Now here is the final little question. The biggest effect that we saw was that M was so much lower at the end of the second stimulus as compared to the end of the first. Why is that? The stimulus itself was the same size. We gave a stimulus current that was the very same size as in the second case as in the first case. Why is M therefore so much lower? Well, it started about the same value. The current stimulus applied was about the same. What was it that was different? So there are two reasons. I'm going to leave these to you. Figure it out. I'll give you a little hint. The first reason has to do with Vm at the start of the first and second stimuli. Look carefully at the value of Vm itself at the start and at the end. The second has to do with the membrane, and in particular the membrane resistance. For a stimulus to create a voltage change, one has to have the current flowing through the membrane resistance. Is the membrane resistance the same during the first stimulus as it is during the second, or is it different? And how would one know that? Well, if you think through these 2 points, you'll have the two answers. Well, that was a thought-provoking segment, a simple observation. When the stimuli are too close together, you don't get a second action potential. Simple observation, but a rather complicated explanation for it all. Thank you for watching. We'll see you again soon in the next segment.